All right, so today we're going to start in on the last chapter of this unit, chapter 7, which is all about alcohols. This chapter will be a little bit shorter than the last one that we did. We'll spend some time today introducing the functional group and then talk about reactions of alcohols to close out the week. Next week will be your second exam, right? So the last class before spring break, which is Wednesday, there is no classes on Friday. So yes, Wednesday of next week will be your second exam, and that'll sort of close out that unit so that you can go into spring break having sort of finished everything off, and then we'll start in our new unit when we get back, okay? So last bit of material to cover here, alcohols. We've talked kind of a little bit about alcohols only insofar as to introduce them. We did have some reactions that produced alcohols as products, but remember, alcohols are any sort of alkyl group with then that OH functional group. All right, so alcohols contain that OH functional group. This thing is also, sort of more specifically referred to as a hydroxyl group, that OH. All right, and we'll talk a little bit about properties of alcohols here in a second, but since we are introducing this new functional group, the first thing that we're going to learn how to do is name it. All right, so we're going to do some alcohol nomenclature here. Okay, so let's just do sort of a simple example. All right, and so we got the same sort of procedure each time that we do our nomenclature. Step one is we got to find that parent chain. All right, so the longest continuous set of carbons. These 1, 2, 3, 4 carbons right here. Okay. Next thing we got to do is name our substituents. All right, and here's our first little bit that we can make note of. We have this group right here, this hydroxyl group. How we refer to that in our name is with the suffix OL ending, OL suffix. Okay, so it's going to go on the end of our parent chain. All right, so I guess just to put two next to each other, if we had just an alkane that was 4 carbons, this would be butane with that OH group on there, with that alcohol group on there. This becomes butanol. All right, so let's just sort of make note here, right? I did still retain the AN. It's not butyl, it's butanol. So there's still that AN, but I have replaced the E with an OL for alcohols. All right, so we're going to put it in the back of our name, this suffix OL for alcohols. We're still going to number our parent chain. Okay, so much like all of our other functional groups, you do have to specify the location of that functional group. Okay, just like we've said before, we can number both ways here. Well, that's not what I want to do. We can number our parent chain both ways. 1, 2, 3, 4, or 1, 2, 3, 4. And so which numbering scheme do we think we want to pick, the red or the blue? The blue, right? Same logic as before. We want to make sure that that functional group has that lowest possible number. So this isn't just butanol, but 2-butanol, right? So then we're going to put it all together. Okay, 2 more examples, and this actually isn't really anything new, but just to sort of remind ourselves. As well as All right, so first of all, alcohol groups we're going to treat just like we did our alkenes and alkynes, in that the parent chain, when you're selecting your parent chain, it must include that OH group. Okay, so we have our list, just like we said before, find parent chain. It must include that OH group. All right, so finishing this one off. Seven carbons with these 1, 2 carbon group here. So see if you can't name this molecule. This would be an ethyl group.
So in this case, it's ender number 2 is no methyl. It's just for the alcohol, right?
Correct. Yep. So this would be 3, then that ethyl group, and then 2, and that's my parent chain there. So the 2 is for the heptanol. Right, that's how I'm referring to the location of that alcohol group, is with that OL at the end of my parent chain name. So 3-ethyl, that part, just like before, you stick your substituent on there with the number in front of it, but then we need to indicate the location of that alcohol group and use that suffix OL. Okay. And then the other thing, which again we've sort of seen before, but just to sort of make note here, I got my parent chain, and when I number my parent chain, I'm going to prioritize that alcohol functional group, something that we saw before with alkenes as well, right? So in this case, I'm not even going to pay attention to that fluoro group. I'm going to number these in such a way that my alcohol gets the lowest possible number. Right? We said that this is what we called prioritizing that functional group. So again, we can just sort of make a note. Our parent chain must include that OH group, but also when numbering our parent chain, we're going to prioritize that OH group. All right, so again, take a minute and see if you can't finish this off. So this one would be 4-fluoro. 2-pentanol. All right, and then one more, well, we'll do a few more examples, but just one more sort of to make note, because always a little bit tricky. If we have a ring, there's only one thing on that ring, so just like we've seen before, we're not going to bother indicating the location, because if I moved it, picked it up and moved it, we would just call that carbon 1. So this is just cyclohexanol. All right, so now I'm gonna put some down and y'all are gonna do this on your own here. Let's see how we do. So let's go through. Very first one, I'm going to find my parent chain. The longest continuous set of carbons is 1, 2, 3, 4, 5, 6, 2, 4, 6, 7. Okay, but what's the problem with this as my parent chain? It doesn't include the OH, right? So my longest continuous set of carbons, that includes that alcohol functional group. 1, 2, 3, 4, 5, 6 here. All right, so that means that this is this 2-carbon ethyl group. All right, and so this is an example of an alcohol where the hydroxyl group, the OH group, is sticking off of that very first carbon, right? So 1, 2, 3, 4, 5, 6. This would be 2-ethyl. I can get my pen going. 2-ethyl, 1-hexanol. Are these all hexanols? Wow, I'm really creative at 8 in the morning here. All right. So this one, again, I'm going to find my parent chain. Okay, I can number my parent chain from left to right or the opposite direction. All right, and which one of these two numbering schemes is going to be correct, the red or the purple? The purple, because remember, the only thing I'm going to do is focus on that OH group. I'm going to prioritize that OH group when picking my numbering scheme. So I don't care about those chlorines. All I care about is the number that the OH group gets. Okay? When I'm putting my name together, how am I going to refer to these 2 chloro groups here? Di. And then the other really tricky thing, remember you got to put the location of both of those chlorines, even if they're on the same carbon, right? So this would be 5, 5, both numbers, dichloro. All right, this is something that people remember to do when they're on different carbons, but as soon as they're on the same carbon, people have a tendency to forget to put both numbers. So it's 5, 5. You got to indicate both of them. Dichloro 3-hexanol. As we sort of noted before, but just to kind of point it out because we see it here, we get commas that separate our numbers, and then dashes separate the letters in the numbers, right? Other than that, we just ram it all together. Cool. And then my last one, same idea, I'm going to find the longest continuous set of carbons, but it has to contain that OH group carbon. And now we just got a bunch of other groups to worry about here. Remember, in our name, we have to have accounted for all the carbons, right? So these are both methyl groups, because they're just one carbon. This is an ethyl group. We're going to number in such a way that prioritizes that alcohol functional group. So 1, 2, 3, 4, 5, 6. Okay. And then I'm going to put my name together. Remember that we got to list our substituents in alphabetical order here. So my ethyl will come first. 2-ethyl. I got 2 methyl groups. They're in different locations. So 3, 4 dimethyl. And then lastly, Y1 hexanol. So 2-ethyl, 3, 4 dimethyl, 1 hexanol. Just rolls off the tongue, huh? All right. So obviously, just like before, the more substituents you have, the more sort of like I don't know, unruly the name gets, and you just got to remember to stick to our procedure, right? So again, the one thing, we kind of made this, remade this list of rules here. We sort of included these alcohol-specific rules. Let's not forget, we always have this was the same as before, but nonetheless, when we construct our name, our substituents are going to be put in alpha order. All right, so introducing alcohols. Again, every time we introduce a new functional group, we want to know how to name that functional group. We'll talk about reactions of alcohols next class. Let's spend a little bit of time just talking about properties of alcohols. Okay. Where you see alcohols most commonly used in the lab is actually as like a solvent. Alcohols, generally speaking, as far as organic compounds go, they tend to be on the cheaper side, which means that you can buy them in large quantities without like breaking the bank. So they make good solvents. You can purchase them in large quantities, so you can use them as solvents. In particular, they would be used as polar solvents. Okay, and back in general chemistry, when you first talked about polarity, it would have been in this very like black and white sort of way. Molecules are either polar or they're non-polar, no in between, right? Turns out that in reality, there's a huge amount of gray area in there, okay? So water would be like the quintessential most polar solvent that you can get. Alcohols are still polar, but they're like one step down, all right? So they're considerably less polar than water, even though they're still considered a polar solvent. So polar solvent, but less polar than water. Okay, and there are a variety of experiments where you would want to really optimize your solvent to solute polarity. So yeah, you wouldn't necessarily want to use something super polar like water. So something kind of in that gray area like an alcohol would be better. Let's talk about what makes gives it these properties. We're going to compare, so we're going to look at the intermolecular forces. And let's just pick this word apart really quick. Intermolecular, right? So that means between molecules. All right, that word intermolecular is just between molecules, intermolecular forces. So these are the interactions between neighboring molecules, right? If I have a sample of alcohol, I have a huge number of actual molecules in there. How are these molecules interacting with one another, right? So intermolecular forces are really interactions between neighboring molecules. And obviously, the forces between interacting neighboring molecules is a very complicated sort of thing. I mean, if you really wanted like a really complete picture, you would have to do some crazy quantum mechanical calculations. One sort of very easy stand-in that's used to measure strength of intermolecular interactions is actually boiling point. Boiling point is a rough measure. Whoa. Of intermolecular forces. All right, and so why is that? Well, let's just think. At the boiling point, a substance goes from what phase to what phase? If I'm boiling something, it starts out as what? A solid, liquid, or a gas? Liquid, and then I'm boiling it, it goes to the gas phase, right? So what's the big difference between the liquid and the gas phase is really how close molecules are. In the liquid phase, these things are still right up against each other, strongly interacting with one another. And then all of a sudden I take it and put it in the gas phase, boom. I had to break whatever force they were using, whatever intermolecular force between these two neighboring molecules, I have to break it in order to go from the liquid phase to the gas phase, right? So where the boiling point of a substance is gives you a rough idea of how strongly those neighboring molecules are interacting with one another. If it's a really high boiling point, that means you have to put in a lot of energy to break these two apart. A really low boiling point means it doesn't take much energy to break them apart at all. Okay? So we can use boiling point as a rough measure for these intermolecular forces. So now let's look at three very similar molecules here and compare their boiling points. We're going to draw out the full Lewis structure just to kind of prove a point here. So this CH4 would of course just be methane. If all of a sudden I take one of those hydrogens and I put on an OH group, now we have methanol. All right, and we're going to compare this to like the most hyperpolar molecule there is, water. What's the boiling point of water in Celsius? Does anybody know? 212 is Fahrenheit, right? And in chemistry, Fahrenheit's like absolutely dead to us. We only use the metric system in the chemistry lab. Celsius is actually a scale that's really built around water, whereas the 0 point in Celsius is the freezing point of water, and 100 degrees Celsius is the boiling point of water. That's actually what the Celsius scale is based off of, is the properties of water. Whoops. So, in terms of boiling point, water with its really strong intermolecular forces is 100 degrees Celsius. Methane, which is actually roughly the same size of water in terms of molecular weight, but it does not have very strong intermolecular forces. The boiling point of methane is negative 165 degrees Celsius, right? More than 250 degrees difference between those two boiling points. I take methane and I swap out a hydrogen and put one of those OH groups, much like we see in water, and all of a sudden my boiling point raises to about 65 degrees Celsius. All right, so which one of these has the weakest intermolecular forces? The methane with its super low boiling point. Water has the highest boiling point here, right? So strong intermolecular forces. And we see that methanol is actually pretty good itself, pretty high boiling point. And all I did was stick that OH group on there, right? So there's something about that OH group that's leading to really strong interactions between neighboring molecules. Okay, and these are what we call hydrogen bonding interactions. Okay, so this OH group right here raises that boiling point significantly because that hydroxyl group is capable of hydrogen bonding which is a fairly strong intermolecular force. And water's got two of them, right? So that's why water is even higher in terms of boiling point, is because it's got two of these O8, or rather two groups here that are capable of hydrogen bonding. All right, so what the heck is hydrogen bonding? Let's talk about that for a sec. All right, and so just to be clear, the name is a little bit of a misnomer. Hydrogen bonding is not any sort of a covalent bond, right? So not covalent bonds. But rather a special name we give to interactions between neighboring molecules, these intermolecular interactions. All right, so it's not a covalent bond, it's just an intermolecular interaction. If we sort of drew out a hydrogen bond here, we're going to have to draw two molecules, right? Because this is an interaction that happens between neighbors. So here's one alcohol group here. Here's another molecule here. All right, and that hydrogen bonding interaction is the interaction between neighboring molecules, specifically the hydrogen of one interacting strongly with the lone pair on a neighboring molecule. Okay, so my hydrogen bonding interaction is this orange interaction here, taking place between the hydrogen on one molecule and the oxygen, specifically the lone pair on the oxygen of one of its neighbors. All right, one important point that we want to point out about hydrogen bonding, it's always going to be true for alcohols because alcohols necessarily have an oxygen, but there are only certain elements that are even capable of hydrogen bonding. They are all the very tiny, very electronegative atoms. So only very small and very electronegative atoms can hydrogen bond. So we got a very short list here based on our periodic table. If we just want to pull up a periodic table real quick, got to be one here somewhere. What's the most electronegative element? Does anybody remember? It's all about fluorine, right? Fluorine is the most electronegative. The closer you are to fluorine, the more electronegative you are. And remember, things get bigger as they go down the periodic table. So the only three elements that are small enough and electronegative enough to participate in any sort of hydrogen bonding are nitrogen, oxygen, and fluorine. Okay? Any other element, even if they have these other criteria that we're going to talk about here, it has to be a nitrogen, oxygen, or a fluorine to be participating in hydrogen bonding. All right, they got to be tiny and they got to be really electronegative. So we can just make our short list here. Oxygen, or I guess we can do it in order. Nitrogen, oxygen, fluorine. Those are the only ones. All right. In terms of our H bonding pair here, we got names for the different ones. The one that's lending that hydrogen in this interaction is called the H bond donor. All right, which means that it has that something bound to hydrogen bond, and again, X is either nitrogen, oxygen, or fluorine. So you gotta have that teeny tiny electronegative element bound to that hydrogen. That hydrogen in that H bond is what's called the H bond donor. The other thing is what's called the H bond acceptor. And the important feature of an H bond acceptor is it has that lone pair on, again, one of those three elements, nitrogen, oxygen, or fluorine. All right, and so alcohols, just like water, have very strong intermolecular interactions. Because just by the nature of that functional group, every alcohol has both a hydrogen bond donor and a hydrogen bond acceptor. Okay. Alcohols, having their very high boiling point, they have both a hydrogen bond donor and a hydrogen bond acceptor. Some molecules just have an acceptor, all right? Basically, we want to be able to spy these features, given this criteria here of what it means to be a hydrogen bond donor and what it means to be a hydrogen bond acceptor. Given a molecular structure, we want to be able to identify whether those sites exist, okay? So let's just look at a random molecule here. right, and we want to identify whether we have any sites that are hydrogen bond donors and any sites that are hydrogen bond acceptors. Okay, this where you have, first of all, does anybody remember what we called this special carbon-oxygen double bond? Carbonyl group. When you have this OH group and a carbonyl group here, this is actually going to be like the last functional group that we cover in this course. This is what's called a carboxylic acid. All right, but let's look at our carboxylic acid and see if we can identify any hydrogen bond donors. And actually, I'm going to draw out the full Lewis structure here, not just the bond line, so we can look at all these carbons. Okay, if I'm going to color my H-bond donors here in blue, do I have any H-bond donors in this molecule?
Yes.
Which one?
The O and the H.
The O and the H. So this one right here, right? It's actually the hydrogen that's involved in that bond. So this would be my H-bond donor. What about these hydrogens over here?
No,
No, why not?
because it's not next to the three that.
It's got to be one of the three, right? It's got to be a nitrogen, an oxygen, or a fluorine. It's got to be tiny and electronegative. Carbon does not make that cut. So no, carbon-hydrogen bonds are not capable of hydrogen bonding. I know that there's a lot of bonds and hydrogens being thrown around in these sentences, all right? But a hydrogen bond is something very specific where you have this electronegative atom bound to that hydrogen. All right? So then just like alcohols, we have a hydrogen bond acceptor site here as well. One of those nice tiny electronegative atoms with its lone pair. Do I have any other hydrogen bond acceptor sites?
Yes.
The one up top, this is that same electronegative element. It's got its lone pairs. There's no hydrogen attached to this particular one, but it could still accept hydrogen bonds from neighboring molecules. All right, let's look at two very similar molecules here. Phosphane, pH3, and ammonia, NH3. Phosphorus and nitrogen are sitting on top of each other on the periodic table, so they both like to have the same number of bonds and the same number of lone pairs. All right, again, if I'm going to go through and I'm going to identify hydrogen bond donors and acceptors, let's look at ammonia first, NH3. Do I have any hydrogen bond donors in this molecule?
I don't think so.
Is it one of my three special elements? Yeah, so this thing's capable of hydrogen bonding. It's nitrogen, right? Nitrogen, oxygen, and fluorine. So yeah, actually all three of these hydrogens here are bound to that teeny tiny electronegative element, nitrogen. So all three of these are capable of hydrogen bonding. So I have three donor sites. Do I have any acceptor sites? Yeah, that lone pair right there, right? So that would be a hydrogen bond acceptor as well. So ammonia, also similar to water, has a relatively high boiling point, even for being how teeny tiny it is. All right, and then what about phosphane, pH3? How many hydrogen bond donors do I have? None. How many hydrogen bond acceptors do I have? None. So it does have this lone pair, but it is just not small or electronegative enough to actually be considered a hydrogen bonding. So this is neither a donor nor an acceptor. It's just not one of those teeny tiny electronegative elements. All right, the bigger an element is, you know, even if you take, for example, chlorine, chlorine's actually about as electronegative as oxygen, but the bigger it is, the more distribution there is for those electrons. So instead of having the electrons concentrated in one tiny place, if it's a big atom, they're just spread out much more. So there's not that same sort of strength of interaction. That's why it's got to be both electronegative, but also very small. So only those three elements in that second row are considered hydrogen bonding, having any sort of hydrogen bonding potential. All right, cool. So we'll next time get into reactions of alcohols. Again, this chapter is not quite as long as the previous two, but yes. So if